Welcome to Chapter 2, where we dive deep into MAGPIE descriptors. MAGPIE, which stands for Materials Agnostic Platform for Informatics and Exploration, is the most widely used composition-based descriptor set. Published by Logan Ward and colleagues at Northwestern University in 2016, it provides a comprehensive representation of any chemical composition. By the end of this chapter, you'll understand the structure of MAGPIE descriptors, know the types of elemental properties used, and understand statistical aggregation principles. You'll gain practical skills in implementing MAGPIE featureizer with Mapminer and performing dimensionality reduction with PCA and TSNE. You'll also learn to design custom statistical functions and analyze feature distributions. The MAGPIE descriptor design is based on three core principles. First, physical interpretability. All features are based on physico-chemical properties of elements, not abstract learned representations. Second, scalability. The same framework applies to any chemical formula with 2 to 10 elements. Third, information maximization. Over 100 dimensions from elemental properties times statistics provides comprehensive description of material space. Ward and colleagues optimized the balance between information content and computational efficiency. Adding too many elemental properties increases redundancy without improving predictions. Too few reduces expressiveness. The chosen dimensionality achieved excellent predictive performance for formation enthalpy prediction in OQMD, comparable to structure-based descriptors. This demonstrates that chemical composition alone contains substantial predictive information. The MAGPIE vector has a hierarchical structure. At the top level, it combines 22 types of elemental properties with 6 types of statistical measures. The elemental properties are grouped into 4 categories: atomic properties, electronic properties, periodic table properties, and thermodynamic properties. Each statistic is applied to each property, creating the full feature vector. Let's break down the dimension count. 22 elemental properties times mean gives 22 dimensions. Similarly, for minimum, maximum, range, and mode, each contributes 22 dimensions. That's over 100 dimensions so far. The remaining dimensions come from weighted averages applied to a subset of properties where composition weighting is particularly meaningful, like atomic weight and ionization energy. Each dimension represents a physical quantity that affects material properties. Mean atomic radius relates to lattice constants and ionic conductivity. Range of electronegativity indicates ionic bonding character and band gap. Maximum melting temperature predicts high temperature stability. Weighted mean valence relates to redox properties and catalytic activity. This interpretability is a key advantage over black box learned representations. Let's examine the 8 atomic properties in detail. These are atomic weight for mass and density effects, atomic radius for packing, covalent radius for bond lengths, density for bulk density estimation, melting T for high temperature stability, column for group position, row for period, and ND valence for d orbital electron count. Atomic weight directly affects mass-related properties like density and phonon frequencies, which in turn affect thermal conductivity. Heavier elements generally reduce phonon velocities. Atomic number is the fundamental element identifier. The Mendeleev number, developed by Pettifer, orders elements by chemical similarity rather than atomic number, placing chemically similar elements close together. This ordering can reveal chemical patterns in material data. Atomic radius is the distance from nucleus to outermost electron shell, affecting crystal lattice size and packing efficiency. Covalent radius is specifically the radius in covalent bonds, typically smaller than atomic radius. These radii determine bond lengths and coordination environments. For example, ionic radius ratio between cation and anion predicts coordination number. Mean atomic radius correlates with lattice constants, while range indicates size mismatch that can cause lattice strain. The 6 electronic properties capture the behavior of electrons in atoms. These are electronegativity measuring electron attracting power, ionization energy for electron removal difficulty, electron affinity for electron acceptance tendency, and the S, P, and F valence electron counts NS valence, NP valence, and NF valence. Electronegativity, typically on the Pauling scale, measures an atom's ability to attract electrons in a chemical bond. Fluorine has the highest value. The difference in electronegativity between atoms determines bond character. Large differences create ionic bonds, small differences create covalent bonds. Valence electrons are the outer shell electrons that participate in bonding. They determine oxidation states, bonding patterns, and chemical reactivity. First, ionization energy is the energy required to remove the outermost electron from a neutral atom. High ionization energy means the atom holds electrons tightly, indicating low reactivity and often noble gas or halogen character. Electron affinity is the energy change when an atom gains an electron. Positive values mean energy is released, indicating favorable electron acceptance. These properties together predict redox behavior and electrochemical properties. The 5 thermodynamic properties relate to energy and stability. G-synergy Pa is the DFT ground state energy per atom, an indicator of crystal stability. G-S bandgap is the ground state bandgap of the element. G-smagmum is the ground state magnetic moment. Boiling T indicates stability in high-temperature processes, and heat capacity relates to heat transport. These properties connect to thermal stability and phase behavior. Melting point indicates the strength of bonds in the crystalline state. High melting point elements like tungsten form stable, hard materials. Mean melting temperature of a composition suggests thermal stability. Density relates to atomic packing efficiency and atomic mass. Low-density materials like lithium enable lightweight applications. Variance in density among constituent elements can indicate phase separation tendencies. Ground state properties come from DFT calculations on elemental crystals. GS bandgap is 0 for metals and non-zero for semiconductors and insulators. G-smagmum captures the magnetic moment, high for ferromagnetic elements like iron, cobalt, and nickel. GS volume Pa is the equilibrium volume per atom. Mode of GS volume can indicate which element type dominates the crystal structure. These DFT-derived values add computational physics insights. Now let's examine the 6 to 7 statistical measures applied to each elemental property. In Mattmaner's MAGPIE preset, there are exactly 6: minimum for the smallest, maximum for the largest, range for the spread, mean for the fraction-weighted average, AVG-dev for average deviation, and mode for the most common value. Each statistic captures different information about the composition. An unweighted mean would treat each element equally regardless of stoichiometry. For Fe2O3, that would average iron and oxygen properties with equal weight. In Mattmaner, however, the MAGPIE mean statistic is already weighted by atomic fraction, so iron gets 40% weight and oxygen gets 60% weight. Weighted mean better represents the actual material composition. For properties like atomic mass, weighted mean directly predicts molecular weight contributions. Minimum captures the smallest elemental value in the composition. This can represent limiting factors, like the smallest atomic radius determining close backing limitations. Maximum captures the largest value, like the highest electronegativity element dominating bond polarity. Range is simply maximum minus minimum and indicates heterogeneity. High range in electronegativity suggests ionic character. High range in atomic radius suggests lattice strain. Mode is the most frequently occurring value, determined by the dominant element's properties. In compositions with one major element and minor dopants, mode captures the host material's properties. Average deviation, or AVG-dev, is the mean absolute deviation from the mean value. It measures how spread out the elemental properties are. High AVG-dev indicates diverse elements with different properties, while low AVG-dev indicates chemically similar elements. Implementing MAGPIE features is straightforward with Mattmaner. Import element property from mapminer.featurizers.composition. Create a featurizer using element property dot from preset with Magpie as the preset. Apply it to your data frame using featurize data frame, specifying the column containing composition strings. The output data frame will have many new columns, one for each Magpie feature, with names like Magpie data mean number. Over 100 dimensions is too many to visualize directly. Dimensionality reduction techniques project high-dimensional data into 2 or 3 dimensions for visualization. We'll cover 3 methods: PCA for linear variance preserving projection, TSNE for preserving local neighborhood structure, and UMAP, which balances local and global structure preservation. These visualizations help understand material space structure. Principal component analysis finds directions of maximum variance in the data. The first principal component captures the most variance, the second captures the next most orthogonal to the first, and so on. For Magpie features, often 10 to 20 components capture most of the variance. The explained variance ratio plot, or SCRI plot, shows diminishing returns. Two-dimensional PCA plots reveal linear relationships and outliers, but may miss nonlinear structure. TSNE, or T-distributed stochastic neighbor embedding, excels at preserving local neighborhood structure. Materials with similar compositions cluster together in the two-dimensional embedding. The perplexity parameter controls the balance between local and global structure. TSNE is excellent for discovering clusters, but doesn't preserve global distances, so cluster positions are arbitrary. It's also computationally expensive for large datasets. UMAP, Uniform Manifold Approximation and Projection, is a modern alternative that preserves both local and global structure better than TSNE while being much faster. The n-neighbors parameter controls local structure preservation, while MNDIST controls how tightly points cluster. UMAP is now the preferred choice for many applications, providing interpretable visualizations where cluster positions are meaningful. Here's a complete workflow. First, standardize features using standard scalar to ensure all dimensions contribute equally. Then apply PCA with n-components equals 2 for visualization. The transformed data can be plotted with Matplotlib, coloring points by target property like formation energy. For TSNE, use Sklern's TSNE with chosen perplexity. For UMAP, install the UMaplearn package and use similar syntax. Compare the visualizations to gain different insights. Understanding which features matter most improves both predictions and scientific insight. We'll cover random forest feature importance based on impurity reduction, permutation importance measuring prediction degradation when features are shuffled, and SHAP values providing game-theoretic importance attribution. These methods answer the question, which elemental properties drive predictions? Random forest provides feature importance as a byproduct of training. For each feature, it calculates the mean decrease in impurity, essentially how much prediction error is reduced when splitting on that feature. Extract importances using model.featureimportances and plot as a bar chart. Typically, electronegativity-related features, atomic radius statistics, and ionization energy rank high for formation energy prediction. This provides physically interpretable insights. Let's summarize Chapter 2. The Magpie descriptor has 132 dimensions from 22 elemental properties times 6 statistics. Properties fall into 4 categories: atomic, electronic, periodic table, and thermodynamic. Each statistic captures different compositional information. Dimensionality reduction with PCA, TSNE, or UMAP enables visualization. Feature importance analysis reveals which properties drive predictions. This understanding helps both in applying and extending Magpie. In Chapter 3, we'll explore elemental property databases and featurizers in depth. We'll compare data sources: Mendeleev with comprehensive experimental data, PyMatGen with materials science focus, and Mapminer with machine learning integration. We'll learn to use multiple featurizer types including element property, stoichiometry, and oxidation states. Finally, we'll create custom featurizers to add domain-specific elemental properties.